Sounds like we're ready. There we go. Take two. All right. Welcome to the absolute last AB unit. This unit is all about area, which we've already studied, volume, which we have not studied, and perimeter, which you think you know, but I will change the way you think about perimeter and arc length forever. We don't need any special effects. It's good, I promise. Okay, so here's the thing though. It's all geometry. Although the title of the course is calculus, it is geometry. Oh, your understanding of what you can do in geometry is going to blow up today. Yeah. And continue to get blown up over the next 12 days when we will officially end the AB unit and get ready for the trimester exam, which is going to be quite the experience. You will need your calculator today. My calculator. Alright, this first model problem, I know you guys already know how to solve this. I know you do. Okay. Find the area bounded between the function f of x equals the square root of x, the x-axis and the vertical lines x equals 1 and x equals 9. For you guys, this should be a super fat, this is the tiniest note I've ever received in my life. Victoria to AP Calc. Okay. Very nice. And I bet you don't even need a calculator for this one. Chepe, I bet you don't even need a calculator for this one.
You never know.
Oh, this is an acid.
Yeah.
Okay.
Yay. That was just practice. Okay. So, I've seen on a whole lot of papers, okay, I'm going to do an integral from 1 to 9, square root of x dx. So that is really, well, gosh, what do? I have to rewrite square root of x as x to the half dx. Antiderivative, you guys all know, is 2/3 x to the 3/2. We evaluate from 1 to 9. You're going to plug in the 9, 2/3 9 to the 3/2. Minus 2/3 1 to the 3/2. So I want you to simplify. Yes, of course. 9 to the 3/2. Take the square root of 9. That's 3. Cube it. What is that? 27. 2/3 of 27 is 18. Minus 2/3. If you do that right, I think you get 52/3. Now, is everybody 100% okay with the setup? The setup is good? Yeah. How do we feel about finding the antiderivative? Finding the antiderivative stuff is good? Yeah. Okay. I also care greatly that we know to plug in and subtract and all of the things. Everybody's okay? The simplifying all the way down to 52/3, honestly, Roger, I don't care that much. But here's what I do care about. Why does this work? You want to stop what you're doing because you're off task in the wrong way. Why does this work? Why do I have all that space over there? Why is this what we do? What have we learned so far?
Based on the
Victoria, what do you
the calculus fundamental theorem. I forgot how it works right, but the reason why we do this is because if we find the antiderivative,
yep.
In other words, the 1 to 9,
yep.
What would happen in the antiderivative is you would find the area.
Yep.
So it would make sense that you would find the antiderivative and then find
So what I hear you saying is you're applying the fundamental theorem of calculus here to say what function has x to the 1/2 as its derivative, and then I evaluate at the top and I evaluate at the bottom and we're done. And the reason that we can do that, Victoria, you're 100% correct, is the fundamental theorem of calculus. But I'm curious, why do we even start this way? Yes, I told you. Yes, my calculus teacher, Mr. Paiva and Professor Scalise told me. But why? Why does it work? Who told them? And don't say they're a high school calculus teacher. I will take my shoe off and throw it at you. Who told us that that is actually the way to find the area? Who did that?
Riemann.
Riemann did that.
Oh, look at that.
What did Riemann tell us to do? Riemann says you want to find this area of the square root of x. Here's the square root of x from 1 to 9. Lucio, what did he tell us to do?
So it's instead of use little rectangles.
You make little rectangles, right? So you make your little rectangles, and maybe it's left endpoint, maybe it's right endpoint, I don't know. But I actually want to see you guys do this. I want to see this rectangle here. I'm going to call it a representative slice. Tells the entire story for the whole unit. I am making a big deal out of it right now. We are going to draw this rectangle again and again and again and again and again and again. Because it tells the whole story for everything else. Sometimes you go back to basics. So, now what did Riemann say? Riemann said, well, if I want to find the area from 1 to 9, what I'm really going to do is I'm going to find the area of a rectangle, right? And in order to do that, you have to say, well, how wide is it? I'm going to call this guy delta x, right? We're going to go all the way back to the beginning. How wide? Delta x. How tall? How do I find the height? How do I find the height of that little rectangle there?
Value of the
It's the value of the function because I'm starting on the x-axis. It's the height, the y value right here. This value, the y value of f of x, I can say that I find the area by doing delta x times f of x. Really, I meant to write that as f of x times delta x. Everybody okay? We find the area of one rectangle by finding the width times the height. One rectangle. But I don't want the area of one rectangle, I want the area of the whole thing. So what am I supposed to do? I make more rectangles. I make more and more and more and more and more rectangles. And what happens is that the delta x gets smaller and smaller and smaller and smaller and smaller. But what winds up happening is at first we say, well, the area is going to be not equal, but approximately, because I'm missing some area here, and even when I make them small, I miss some area, right? We would say it's going to be like f of x1 times delta x plus the area for my next rectangle times delta x plus the area for my next rectangle times delta x. And I'm going to go all the way until I get to that last one. It's a height times a width, a height times a width, a height times a width. Because they all have the same pattern, there's a better way to write this. Right? We use sigma notation. We say, oh, it's f, f is right. F of x1 times delta x, f of x2 times delta x. They all have this form, f of x sub I times delta x. The sigma just means sum. Add them all up. Still an approximation. We're okay? But how do I get the exact right area? You guys know how to get this. How do we find the exact right area, not an estimate to the area? I want to hear from somebody over here. How do you get the exact area? You take the limit as n approaches infinity. So your area is found by taking the limit as n approaches infinity of this sum. F of x sub I times delta x. Now, in our entire time together, we have actually gone through and done this computation twice. Both times it took about 30 minutes. Yeah.
Aren't you missing one thing from that?
Aren't I missing one thing?
Don't you have to start off by like n, the number of rectangles?
But that's built into the delta x, right? Because delta x is the width. So as I bring in more rectangles, the width gets narrower.
Oh.
Big picture, we're okay?
Yeah.
So this is what's happening behind the scenes all the time, right? But what we really do is you're like, okay, I know there's like a little bit of a leap here. That all we really have to do is find the definite integral from a to b, from my start to my end, of my function, times dx. But I want to remember forever y f of x, because that's the height of a rectangle slice. Y delta x, because it's the width of the rectangle slice. Y, the 1 and the 9, because it's my start point and my end point. This idea over here, we're going to come back to it with volume, with perimeter, with all the things. Big picture, everybody okay? Any questions? All right, so show me you guys what you can do. Show me what you can do with the next one. Well, I go Mark Roger absent. You don't have to go all the way through the craziness. Find the area of in the first quadrant bounded by the curve f of x equals negative x cubed plus 9x on the x-axis. Once you complete the problem by hand, you can verify the results with your calculator. So lots of beautiful math happening here. I've seen a whole lot of folks, and normally what happens in like the AB class, we get here and we get stuck. Why are they getting stuck? Maybe not so much you guys. But why are people get sometimes people get stuck here? Why do people get stuck here?
I guess because you don't have where the x.
Right, I didn't give you the, what are they called?
Limits of integration.
Yeah.
The limits of integration, right? I didn't give you the x values. And they're like, oh, okay, fine, I need to go get them. And they get over here and they're like, yeah, I don't remember what the graph looks like. Okay, fine. But the important thing is whatever the graph looks like, I need the roots. And so I know I saw a lot of factoring happening. So you've got like negative x times x squared minus 9, x plus 3 times x minus 3. If that's going to equal 0, then x equals 0, x equals negative 3, and x equals positive 3. Now that should give you a nice sketch. If you remember from pre-calc, you've got 1, 2, 3 roots, negative 3, 0, and 3, you've got a cubic polynomial, odd degree. Leading coefficient is negative. We have to know what the graph looks like. Think about odd degree. Remember, like we do like this thing, and sometimes the polynomial bounced off the x-axis, sometimes it passed through. So if it's x cubed, what are the tails doing? If it's x cubed, from your perspective, it should do like this thing, right? This tail points down, this one points up. But I've got negative x cubed, so the tails have to do this thing.
Yeah.
So your graph ought to look something like that. And we're not going to let ourselves get obsessed over how high up and how far down, just a sketch. Okay? So now I want in the first quadrant. So we're going to go from 0 to 3. How many of you guys had this as your setup? Integral from 0 to 3. We're okay? Alright, we'll kind of fast forward. So the antiderivative of negative x cubed is negative a fourth x to the fourth plus 9/2 x squared. Evaluate from 0 to 3. Plug in the 3 first. Negative a fourth, 3 to the fourth, 9/2, 3 squared. Minus, plug in 0. We're all friends here. We know that's 0. 3 to the fourth is 81. Negative 81 over 4. 81/2. I think if I haven't messed this up, 81/4.
Yeah.
81/4. On the calculator, you get like 20.25. Everybody okay? These two problems are the things that you should be comfortable with based on what we've done in AB. Now it's time for the push. Both of these problems had something in common.
Numbers.
The numbers? Yes, we've used numbers.
Bounded by the x-axis.
Okay. We've been bounded by the x-axis in both cases. I am no longer going to require the x-axis to be a bound. We're going to go differently. We're going to go deeper. All I want you to do is trust your smarticle particles. That's all you got to do. Victoria, can you read the area between two curves, please?
We can now extend this idea to regions bounded between two or more curves. Once we get the big idea under control, we can then expand upon our thinking and explore more interesting problems, such as areas bounded by 3 curves,
Oh God, I love those.
areas bounded by curves which are not functions,
Oh my God, even better.
areas formed when curves intersect more than 2 times,
I don't like this so much.
and the list goes on and on.
Okay,
Can we?
Continue.
yeah, keep going.
Over the course of the next few days,
Which in BC means for the next 10 minutes. Yep.
we are all going to master the big idea of area bounded by multiple curves. For today, you can use your calculator to set up as well as evaluate the definite integral. Starting tomorrow, you will not be allowed to use your calculator.
All right, excellent. All I want you to do is trust your smarticle particles. Trust your smarticle particles. For those of you that need a process, there's one there in the box. Read it later. I just want you to trust the smarticle particles here. Have faith. It's all going to work out okay. So a typical problem looks like this. Find the total area bounded by the curves f of x equals negative 2x squared plus 3 and g of x equals negative x plus 2. This is the new challenge. This is how these problems will look and feel and present themselves. I'll give you a minute or two to get your legs underneath you and come up with some ideas. The less you use your calculator today, the better. If you need your calculator, it's okay, no judging. Won't
So
judge you,
you
Nathan,
look
not at
something
all.
like that.
So here's my request. Yeah.
Oh,
Wait, just a photograph.
I was just like creating
That's a
a
lot for me to expect you to do this one, right?
I was just saying that that's what
There's a
it's gonna
multiple
be.
choice section.
So, you know, it's
So we're going to
fine.
find this area.
Yeah, whatever it's here.
Can we just subtract? Or we find the intersections, can we?
Do you find the just
So we
intersection?
find the 2 intersections, and just subtract the area of this, of the curve minus area of area of this minus area of that. Because it's an intersection here.
Okay, if that's what you want to do, that's fine. Know that you can have until Thursday.
Do we just off? Unless we,
Oh, here's it.
unless we set it equal to each other, then you can find. Where it says.
Okay.
So then you'll be fine. After we first
Alright,
have
so
to
what are
find
the
where they
thoughts so far?
intersect, right?
Yeah.
Guys,
That's
plugging zero to see where these equations
Looks that lazy.
move into
I mean, I get the
the
idea.
exactly.
Yeah, we're just trying to
Okay.
save our energy.
Okay.
It's okay.
I'm not
Just
really
use
sure
the
what you're doing with the
calculus
zero there.
and attack the-
Oh wait, you said to find out like where they cross the y-axis?
Yeah,
We
that's
do,
Okay.
we do 2x squared
So
plus 3 was
you want to see where they both intersect and
How do you find it?
I didn't even say that, alright. I just want the total area bounded by these two.
Was it
Menu.
Now, I was kind, I was kind
Just
in
like
that I
picture.
deliberately picked graphs that you guys should know what they look like. Right, f of x equals negative 2x squared plus 3, we know that this is a parabola.
Yeah.
Opening which way?
Down.
down?
Opening down with the vertex
Alright.
at 0, 3. So here it is.
Yeah.
This is f of x equals negative 2x squared plus 3. Oh my gosh, I was even kinder. G of x equals negative x plus 2.
Linear.
So that's a line going like
Yeah.
that. it would be a good idea to use the colors. I really think a little bit of shading is going to go a long way here. Because part of the issue is going to be, what am I even asking you to find? Which area is this? Right? Specifically the area bounded by the curves f of x equals negative 2x squared plus 3 and g of x equals negative x plus 2. Where is that?
When it says bounded, I think of like where it's
Intersection.
Bounded, definitely intersections are going to be in
it's
there.
like a closed
Right,
area.
bounded, I want you to think closed. I want you to think trapped, like maybe how you're feeling right now. You are trapped in here with me. You're bounded. Well, what area is bounded by the two curves?
Above the above gx, but
Above G
underneath.
but below F? Is
Yeah.
everybody okay? So this is the area that I want. Rules have suddenly changed. Normally, you're bounding by the x-axis, by the function, from a place to a place. Not the case anymore. But what?
You still can't.
Now, depending on how you see this geometrically, you have there's some things that you can do. I want to take you through the process. Is everybody okay that the intersection points are going to be important?
Yeah.
Right? Like we need these two to figure out where do I start and where do I end.
Yeah.
For right now, I'm just going to label them as A and B. You guys know, like we're going to come back to that in a little bit. But what's the setup?
So what you think here again?
Well, what I want is the area bounded between the two of them. And the secret is that representative slice. That thing I made a big deal about before. Make a slice. I'm going to make my slice this way right now. No, not for pizza. I'm going to slice up my area this way. And my question is, how do I find the area of a little slice? Well, I've got a thickness, a little dx thickness. How tall is that rectangle?
I think G of X.
Is it f of x tall?
No, G of X minus F of X.
F of x tall means I'd start here on the x-axis and go all the way up to the curve f of x. G of x tall means I'd start over here and go all the way up to the line.
So
I want this part in here in between the two of them. What do I want?
I
I want f of x minus g of x. I want the top function minus the bottom function. That's how I'm going to find the height there. Anthony, you okay? Yeah. So my setup is going to involve the integral of f of x minus g of x with respect to x. Not just f of x, because that would say go down to the x-axis. Not just g of x, because that would mean go down to the x-axis over there as well. But I look at my slice, my little representative slice, and I say, how thick is it? It's my dx thickness. How tall is it? The height is measured by the difference in the y values. Y value here minus y value over here.
Yeah.
Big picture, we okay? So I need the intersection points, that's a thing. How am I going to get the intersection points? If I take your calculator away, Chepe, what are you going to do?
Set it equal to each other.
You're going to set the two functions equal to each other. That's how we find intersection points. Great.
These are algebra.
Right? So a little bit of algebra. Negative 2x squared plus 3 equals negative x plus 2. Let's see, it's quadratic. I like my quadratics to have a positive leading coefficient. So I'm going to move things there. 2x squared minus x minus 1. Depending on how you factor, maybe you factor this way. So I think the intersection points are negative a half and 1. If you want to confirm those on your calculator, feel free.
I've got negative 0.5.
You get negative 0.5, which some of us even know that to be negative a half.
Watch it over.
Okay? Alright, so your setup is to go from negative a half to 1 f of x minus g of x. And if you were going to do this on your calculator, you could just say, well, f of x, I'm going to call this like f1 of x. I'm going to call this guy over here f2 of x. And I'd say in an integral from negative a half to 1, f1 of x minus f2 of x
But doesn't that only apply to that one little rectangle?
Tell me more about that.
Because the line of g of x, it's not a horizontal line,
Yep,
like the x-axis.
yep,
Which means that even though you selected that one rectangle,
yep.
the rest of the rectangles aren't going to be the same size.
Oh, I like that. So what I hear you saying is, although I drew this rectangle, they all have different sizes. Are we okay with that? But the key, Victoria, is how did I figure out the height of this rectangle? What did you do?
So I subtracted f of x minus g of x.
F of x minus g of x, whatever the y value is here minus whatever the y value is here. How would you do it if the rectangle was over here?
Oh, I did the same way.
It would still be f of x minus g of x. What if I did it over here? F of x minus g of x. It has the same form. That's why it's a representative slice. This slice could be any slice. Okay? All right, so while you guys finish that off on your calculator, I'm going to go through and finish this off by hand. Okay, let's get the right number here. So integral negative a half to 1, get negative 2x squared plus 3 minus x plus 2 dx. I think that's 27 over 24, which is 9 over 8.
Better.
1.125?
Yeah.
1.125 on the calculator.
Yeah.
Okay. What are the questions that are out there? There is really a big idea here. And once we get this under control, you guys are good to practice and play around with this, and all the points are going to run down. Jose?
With these three problems, are we going to do multiple equations?
What do you mean multiple equations?
Like 3 equations intersect?
Oh my god, yes! Won't that be wonderful if there's like more intersection points? Or, oh my god, what if the way that you talk about the representative rectangle over here changes from like when you do it over here? Yeah, that would be good too. These are really good ideas. But the big idea is draw your little slice and do a little top minus bottom. That's it. Yeah.
Will this occur in all of our functions? When you're trying to solve for the area, will it do like the same process on all of our functions?
Yeah. Except when it doesn't work. In which case you try something else.
Calculate.
Okay. Everybody okay? Nathan, you alright? Okay. Alright, so sometimes you're going to get to use your calculator, sometimes you're not going to get to use your calculator. Sometimes it's going to be one region, sometimes it's going to be multiple regions. Trust your instincts. Alright. Time for you guys to get a little bit of practice. Determine the total area bounded by the curves f of x equals tangent of x over 4, g of x equals 5 minus e to the x over 2, and the y-axis. 100% calculator active. 100% calculator active.
What area would that be?
Each of the regions.
I don't know what area it is.
Jose, if I ever had you drive the laptop,
Oh yeah. Okay.
would you be okay with doing that?
Yeah.
Okay.
Or is this really degrees or
Radius.
radians?
Brian, he always knows the area.
students take their test outside one time with their supply on.
What? I do not have my time wasted. No. Okay. Just a second.
So this is time where it wouldn't work using our method.
What's your method?
No, the one that we're doing right now. The method that we're doing right now.
We'll make the curves for region.
I don't know. We'll find out. Have faith. Have faith. Yes, a good thing to do. Really strongly encourage the shading in the beginning. What region are we talking about? Look at the bounds. And the y-axis sort of has to be this piece over here. Okay. So one of the challenges we're going to run into in this unit is what region are they actually even talking about? Because it's going to make a difference. Okay. Okay, good. So we've got the right region. Don't go too crazy on the shading. Jose, in order to get the E, you're going to have to use the exponential button, this guy over here. There you go. Okay. So,
They're only focused on the
what was that, Chepe?
They're only focused on the that you gave them graph.
If you want to. Okay, Chepe, before I do anything else, is everybody okay? This is the region that I'm interested in.
Yeah.
Victoria, Lucio, you get this is the region? Like, it might seem obvious, but it is worth just taking a couple of seconds to be like, okay, this is the region. So here's what I care about. If this is the region, and it is, well, how am I going to find that area? Sure, you're going to use your calculator, but we now have to do a definite integral. From where to where? From 0 until I hit this intersection point, right?
So from 0 to 1?
Now here's why I want to be careful. I do not want you to use your eyes to tell me where the intersection is. I want you to use your calculator. You remember how to find the intersection point?
Yeah.
And this unit, especially more than anywhere else before, you have to store those values so that you can maintain your decimal point accuracy. We're going to say, all right, we're going to go from 0 until, what is that, 2.841? Okay, so just jot it down on the side, from 0 to A, where A is this 2.841. 0 to A. Now I need an integrand. Good. How can you move, what is it that you're trying to move?
So it's not all overlap.
Yeah, you should be able to move them. You have to do the control and then close the fist.
Oh.
So control and then hit the button. And that should... Okay, check it, hold on. Hit escape.
Would we put the value of A or B?
Okay, hold on. And now move the pointer. Move the pointer so that it changes from a pointer, whatever it is that you're trying to grab. Now hit control. And it changes from an open hand. I think you do control and then this guy here, and it changes to a closed fist so you can move it.
Oh, okay.
Okay?
Yeah. Would this value be A or B?
What do you mean A or B?
Because you know how usually like you store the value.
Uh-huh. So what do you store it as? It doesn't matter to me. You can call it A, Brian can call it D, it doesn't matter. But make sure it's clear what you're calling it. Now the next question is, what's the integrand? The answer is, tell me about a slice. How do you find the width of the slice? The width is dx. How do we find the height? And this is where I want to be really careful. Depending on how you labeled your graphs, the one that's coming down this way is g of x. So that representative slice has a height of g of x minus f of x, and you have to write it that way. So it's going to be the integral from 0 to a g of x minus f of x dx. And if I'm scoring this, like I'll probably score your quizzes, you'll get 1 point for the right limits of integration. You'll get another point for the integrand. And then the last point is, what's the right number? I would also encourage you, do not do any of your calculations. Don't do any integration on the graph screen. So you're going to hit the little toggle button, Chepe, so that you can go back over to the calculate screen and now just do all the calculating in one place.
I'm still kind of confused with the little part in here. I don't know understand how you say it.
What was A?
Well, A, oh, did you not store it?
No.
Okay, 2.8413. So, Anthony, I'm trying to figure out how long that slice is. In geometry, the way that you find the length of a vertical slice is the top y value minus the bottom y value. Top minus bottom.
Okay.
So, right, F2, open parentheses, x. Now I'm a little worried because your F2 is not bold. Something's wrong here. If it's a function that you've already typed in, the F2 should switch to bold.
Oh, mine's not bold.
Yeah.
It's on the.
And that's
Yeah, did you do the work over on like the scratch pad side?
right there.
That's the problem.
No.
Yeah.
Yeah, sorry.
Yeah, usually for calc, I never do anything over in the scratch pad side, I just do it over on this main side. Okay, this is not going as smoothly as I was hoping. Can we get a value? So you're going to go over here and do the calculations. So from 0 to 2.8413.
I just said 3.6.
You've got what? Wait.
No, it's because I was looking at the time.
Oh, okay.
Oh, that's 6.819.
I'm looking at the time too. So we've got 6.8194.
Yeah, sure.
6.8193.
6.8193. Okay, the reason that we're getting a little bit different answers is we're not maintaining the decimal accuracy. I really need to see you guys store those intersection points. So it looks like your final answer is going to be 6.8139. Right, 6.8193. 93. My apologies. All right, see what you guys can do with the next one.
What if we go ahead and round, like from 3.8 to 4?
From 3.8 to 4, that's fine, as long as it's 3 decimal places. What I don't want to see happening though, I don't want to see you rounding here.
Okay.
Because you need this value to do more calculations, and if you round early, it's going to get all messed up. Determine the total area bounded by the curves f of x equals that from 1 to 4.
What are we doing?
So I want the total area bounded by the curves f of x, g
GMX on the
Like
overall.
overall.
No. We're supposed to be,
Yeah.
it's supposed to be this region. That's bounded. This thing is bounded by both this function, which is
So are we supposed to
do it obviously and the tangent. These are two, not the x-axis. This one is the x-axis. And both there.
Yeah.
So finding the right region is definitely going to be a problem. I need the area bounded by f of x, g of x, x equals 1 and x equals 4. That has to be this little region over here that we've already played around with. And there's another one that comes down here. Right. What's different now is we're not using the x-axis as a bound. It's not one of the boundaries. The boundaries are the things that they tell you. So you've got f of x as a boundary. I guess f of x is the blue one. G of x is a boundary. X equals 1 and x equals 4, but no longer the x-axis. So one mistake that I'm seeing is some folks just saying, let's go from 1 to 4. Why not? Victoria, why isn't that going to
So
work?
because the reason we did it the first time was because it was just one certain area that was enclosed, and
Yeah.
whatever the function that we created, it made sense for all of it. In this case, if we create a function, I don't think it would apply to all parts of the shaded area.
Okay, and you're saying function,
Or
and really what I want you to think about is it's that slice, right?
Yeah.
It's that little rectangle slice that we're talking about. How do I find how long that rectangle slice is over here?
that's when we did the G of X.
It's red minus blue, so what is that? G of x minus f of x? But once I pass this intersection point, it's not g of x minus f of x, it has to switch now to f of x minus g of x. You have, the way that you're going to make all of these decisions, it's going to be that little representative slice. So I'm going to have to do an integral, not from 1 to 4, but from 1 to a.
Yeah.
And this first one is g of x minus f of x dx. And then the next one should be the integral from a to 4, f of x minus g of x dx. That's really the thing that I care about. Take a little bit of time to sketch out the region. It's going to go a long way. Chepe, what's happening over there? You're trying to store. So click on it. Okay, hold on. Hit escape. Hit escape. Okay, go over to the intersection point. Go. No, don't turn off my computer. Go back to your graph. Sweet, giblets. Okay, go back to the intersection point, click on it once, and then hit stop. I'm sorry, bar. Bar, store bar, call it something. And you have to write down on your paper somewhere what that variable is. Okay, good. And all like the heavy lifting is happening over here and like figuring out the intersection, figuring out the slice. Once you get here, it's like one step into the calculator. You got it? 5.30.
Yeah.
12.30. Okay, keep going. It just gets better. So Chippe, you call it H? Okay. There's something that you're doing right now that I'm not a big fan of.
If you went to
Anybody else see it?
is it because he's not using the graph that already comes with the calculator?
Right, it's the 0 that's the problem.
Oh.
Right, you've got to go from 1 to H. The best advice I can give you is ignore Scratchpad. You don't need Scratchpad. Everything that we need lives in the calculate and graph screens. Did you get 5.3 over? Nice, keep going.
I had like 8.
We follow one
I had
time.
8.
So my advice for you, Chepe, one time to the calculator. Right, you don't have to be kind and be like, oh, my calculator can't handle it. Yes, it can. Like, I want all the thinking to happen with the setup and then get to autopilot.
This is what I mean.
I hate when it says bounded below. It's on Mars. The wording gets in there.
And that's going to be a thing in this unit. Good. That's the region.
No, I mean like.
That's not the answer.
No, wait, that's only region.
Yes.
Oh.
Okay. So, Chepe, what do you think the final answer is? I don't agree.
What?
I'm sorry, sir, I don't agree.
Why is there so many things?
So from 1 to H, and from H to 4.
Oh, he did.
Oh, you switched
yeah.
them.
Oh, I switched the variable.
It's got to be F minus G. Okay, wait, let's teach you some, Chepe. Stop! Stop! Now I remember why I don't have you do this. Escape. Delete.
Delete.
Chepe, don't make me go back there and hit the delete button myself. No, just delete the, oh my God, delete all this. I'm trying to teach you something. Okay, arrow up.
Why do you have it as H?
Oh.
Now hit enter.
Like that.
Oh my God. Teach the seniors, they're great.
It's DUS Pillbrook on the app.
With the best.
Now hit enter, 5.303, thank you baby Jesus. Okay, moving on. Oh, so sad. So sad, Brian doesn't know where the line y equals -2 lives.
Wait, oh.
Oh.
Right.
All right, Chepe, you got one more in you?
And you're in BC, man.
Okay.
What region is this? Is this region is?
Sorry, what happened?
Is this region is?
Oh, you see it or?
How do you do this thing? How do you switch this?
What do you mean how you choose it?
Like, how do you know where to put it exactly?
This is like,
Oh, it's just a random rectangle. Because I know this is region is.
Okay, so you've got the right region.
Okay.
Good. We've locked in on the right region. Now the problem is, how would you find that area? There are some new challenges in this region.
Oh, I know how to. I feel like I know how to do it.
with the function of the instead of y equals -2.
Okay, so one of the challenges is you need to figure out new intersection points, right? You've already got this guy up here that we're already calling A, but you are going to have to figure out these as well. Another problem? What about those slices this time? Think about those representative rectangles. There's something different this time.
They're horizontal. No, vertical.
They are vertical. But if I draw a rectangle over here, how do I figure out the height?
F of x minus 2.
Be careful, not f of x minus 2.
Plus 2.
F of x minus -2, top minus bottom. Right, in this case it will become f of x plus 2, but f of x minus a -2 is probably a safer way to think about that. And that's the length over here, and over here, and over here, and over here, and over here, but not over here.
G of x minus -2.
Right, over here, once you pass this intersection point, your representative slice changes to being g of x minus negative 2 or g of x plus 2. You have to use two completely different integrals because your slices are different now. But it always comes back to the slice. So for this last one,
Find the intersection.
right, so I need, what is it, f of x plus 2 dx, find that area. Then g of x plus 2 dx, find that area. I think we know one of these intersection points already, or one of these limits of integration.
No.
Look at the region, look at your sketch.
A that you had.
The A that we had
That's
before.
We don't know the first one, but it's from something to A.
Okay, good. We know it's from something to A. I'm going to have to get the something by doing an intersection point. And good, so Chepe, you threw in that horizontal line at y equals negative 2.
Yeah.
So that now you can find the intersection point. And you are going to have to identify which of the two graphs we're talking about. And so on my graph, if I've got a new intersection point in town, I'm going to say, okay, so B is, what is this, negative 4.4286? As these regions get more and more and more complicated, it is that much more important to label, to store, to make your life better. So this guy over here is going to be an integral from B to A. And now on the second integral, that intersection point is where I start integrating. And I'm going to go from B, and it looks like Chepe thinks that this last intersection point is 3.8918. So I'm going to do the integral from A to C, g of x plus 2. Last thing for me to do, type it into my calculator, have the calculator do all the work.
Wait. For A, is A, no. So what's B?
A, so for me, B is this intersection point over here, the negative 4.4286, and the C is this 3.8918. Right, you can label it any way you want to, but you have to tell me clearly on your paper what it is. Anybody get a number answer yet? Okay, let's just get that typed into the calculator and we'll call it a day. Oh, you're still over in the scratch pad.
Flashback?
Yeah, that will be his best friend.
It's a different one. See?
14.06.
Okay, Brian thinks 14.06. 14.0616. Maybe.
That's the answer.
Okay, we've got 14.6. No, that's not the answer that you have, you big liar.
Yeah, 14.0.
14.0616.
Yes, sir.
Yeah.
Okay. What we're going to focus on for the next 12 days, it's all geometry, and I kid you not. Come on in.
Wait,
It all goes back to that little representative slice. Okay. Now, for those of you that are going to turn the page over and you're going to see some stuff labeled homework, that is absolutely not your homework. You can turn it off.